everyone, my name is Logan and welcome back to the lecture hall. Today we are covering section 11.8, power series. And so we begin with what even are power series? Well, they're series of the form C sub n times x to the n, and this would then come out to be CO, initial, plus C1 x1 plus C2 x squared plus C3 x cubed, and it's essentially just a series that also has another variable with x, where x increases by a power each time. And so now we have the definition of a power series centered at A, and this would be the sum from 1 to infinity of C sub n times x minus a to the n, where this comes out to C initial plus C1 times x minus a plus C2 times x minus a squared plus C3 times x minus a cubed. And so these are two forms of power series. Essentially, this is the more general form centered at A. This would be a normal power series, or, well, just a power series, where this would be centered at 0, right? Because x minus 0 to the n is the same thing as x to the n. So why do we even need power series? Why are we like, yes, we want them? Well, because we can use power series to help represent our functions. So for example, in the textbook that I pulled it from, we can use a power series to represent the Bessel function. You don't need to know what the Bessel function is, but it's just a way to show series, or I guess functions in terms of series, and it's a way to possibly visualize, break it down, approximate, whatever it may be. We just use power series to approximate functions. So this brings us to the first theorem of our video, and it's theorem 1. For a given power series, the sum from 1 to infinity of C sub n times x minus a to the n. Also, quick note, C sub n does not necessarily have to just be some constant like 1 or 2 or 3. It can be another portion of a series, maybe square root n or 1 over the square root n. Well, if we have a given power series, there are 3 possibilities. The series either converges when x equals a. And so that would make immediate sense, right? Because x equals a, well, a minus a, 0. Then we just sum up a bunch of zeros and it sums to 0. Next, the series converges for all x. This may be the case when C sub n is a big, or I guess very small thing on a denominator, or maybe a big thing in a denominator, so it's a small number, but the denominator gets huge. I don't know if that made sense to you guys. And then there is a number r such that the series converges if x minus a is less than r, and diverges if x minus a is greater than r. And so this r is very important. This r is going to be called the radius of convergence. And essentially, that is how big your x can stray away so that our series still converges. And so then we have this r, which is our radius of convergence, and from there we can create our interval of convergence, which we will go into now. Now, on to radius of convergence and interval of convergence. If we have the interval, or I guess the inequality, our x minus a, which is less than r in absolute values, well then we have a minus r is less than x, which is less than a plus r. And we can then get 4 possible intervals based upon our use of parentheses or brackets. Parentheses, as we know, for interval notation means that number is not included. For brackets, it means our number is included. How do we test if numbers are included or not? Well, we plug in set x for the series and see if it converges. It's not too complex. And so now we have some examples to kind of get a better idea of what these could possibly mean. Well, we have the series x to the n, the radius of convergence is going to be 1. And our interval of convergence is going to go from -1 to 1 without including them. Now, if we have the series n factorial times x to the n, well, the n factorial is on the numerator, there is no denominator, and n factorial grows immensely fast. So it should be obvious that the radius of convergence is 0, because there really should be no numbers that make this converge other than 0. And so our interval of convergence is actually just going to be the set with one element, 0. Now we move on further and we have the series x minus 3 to the n over n. Well, our radius here is going to be 1 as well. And now our interval of convergence is going to be a little different because we have this x minus 3 to the n. Well, it's going to be from 2 to 4, where 2 is included and 4 is not. And how do we find that? Well, as I said, we plug the endpoints into our series and then test from there, see if they converge. Finally, we have negative 1 to the n times x to the 2n divided by 2 to the 2n divided by, or times n factorial squared. Well, the radius of convergence is going to be infinity on this one. It doesn't matter what value of x we plug in, it will always converge for this series. So then, well, if our radius is infinity, what is our interval? Well, our interval is clearly going to be negative infinity to positive infinity, where we use parentheses because infinity is not really a real number. So infinity is not included, but it's the closest thing that we can get to it. So now this brings up the question of how do we even figure out our radius of convergence and our interval of convergence? Well, we use the root and ratio tests. And how, you say, well, how? Well, we know that if something is less than 1, when I say something is less than 1, when we get a root or ratio test that ends up being less than 1, then we know our series converges. If it's greater than 1, it diverges, and if it equals 1, we can't say anything about it. So, for both, we are going to plug these into our root and ratio tests and see what we come up with and try to solve for an inequality where we get something less than 1, and then we solve from there and we can get our radius and our intervals. Now, if we were given the series negative 3 to the n times x to the n, all divided by the square root of n plus 1, and we were tasked with finding its radius of convergence and interval of convergence, how would we do that? Well, as I said in the previous section of this video, fancy little jump cut, I know, that our limit as n approaches infinity of a to the n plus 1 over a sub n, that's going to be our ratio test, and we are able to use our ratio and root tests to then solve for our intervals, or I guess our radii of convergence, and then our intervals, or I guess radius of convergence, because there's only one radius. And so how do we do that? Well, we take a sub n plus 1 term, divide it by the a sub n term. Well, this is not too bad. This is going to be negative 3 to the n plus 1, x to the n plus 1, naturally, over the square root of n plus 2, because n plus 1 is n plus 2. And now we're going to multiply it by, well, we want to divide by a sub n. So if we multiply by the reciprocal, that is the same thing as dividing by itself. So then this is divided by root n plus 1 over negative 3 to the n times x to the n. And now we're like, okay, we've done this stuff before, and we take the limit, but I don't want to write that right now. So we're like, well, this negative 3 to the n can cancel with this negative 3 to the n plus 1 and just leave a 3 over. And then the same thing can be done with the x to the n and the x to the n plus 1. And then we get that this is equal to the limit, now I'm writing, as n approaches infinity, of negative 3x times root n plus 1 over root n plus 2. And so if we take the limit, well, these are the same powers. This is n to the 1/2 on both accounts, and those are going to diverge to 1. So then we get, I guess, well, we get 1 over 1, right, because they grow at the same rate because they're both square root functions. So we then get, well, once we do this limit as n goes to infinity, this is negative 3x absolute values. And we want this to be less than 1. Why is that? Well, because that's how we find our radius of convergence. And then we're like, okay, well, this negative 3 can just come out in front, and then we get, well, 3x. 3 times absolute value of x, which we can then divide by 3, and we get that x is, the absolute value is going to be less than or equal to 1/3. Well, this will give us then our radius. We can say that our radius of convergence is 1/3. And now we need to figure out what our interval is. Well, we start with our interval quite easily because this is the absolute values, right? So then we plug in, well then this would be -1/3 is less than x, which is less than 1/3. And so these two statements are equivalent. So this is going to be our interval of convergence, but we are not done. We actually have to plug these in to solve and see if they converge with these numbers. Now that we've found our radius of convergence and a portion of our interval of convergence, this -1/3 to 1/3, we need to figure out, do we put brackets or do we put parentheses around these things? And so how do we do that? Well, as I said beforehand, you just plug in your x's, and specifically the endpoints of your x's. So we're going to plug in a -1/3, and this is to the nth, because this is just x to the n, -1/3 to the n. Well, this then becomes, well, -3 times -1/3, both to the n. This is just going to be equal to the sum of 1/√n plus 1, which we know diverges because this is a less than a power 1, and whenever, I guess what I should say is 1/n, the series diverges when 1/n to the p for a power, not a power series, but this n to a pth power, if that p power is less than or equal to 1, the series will diverge. Well, this is a square root, so that's n to the 1/2 essentially, because when our numbers get really big, we don't have to worry about this plus 1. So this diverges. So then we can say, well, if that diverges at -1/3, we can put a parenthesis. Next, we do it again, but now for our big endpoint, or I guess our larger, maybe more, well, our positive endpoint, because technically they are the same magnitude, just different absolute value. So we then figure this, well, this is 1/3. And this then becomes the sum of -1 to the n over the square root of n plus 1. And that is actually convergent by the alternating series test. Work phone just went off, by the way. So now we're like, okay, well, what is the alternating series test? I made a video on it. Go watch it right now. I don't think it had the poll in it. So I will let you guys check by the alternating series test. But we then found that our interval of convergence is parenthesis -1/3, comma 1/3 bracket. So then that means -1/3 is not included in the convergence, but +1/3 is included in the convergence. So that's all I wanted to cover for the lecture portion of today's video. Let us transition to some practice problems. We're just going to do one very quick example because I'm running out of time. My time management was a little off. Woke up maybe a few hours after my alarm was supposed to go off. Who said that? So we're doing number 18. And this is the sum from 1 to infinity of the square root of n times x plus 6 to the n, all divided by 8. We're like, okay, we do the ratio test on this, and then we'll see what happens. Well, if we give a little bit bigger, or I guess deeper thought to this series, we see something. We see this times square root of n on the top, on the numerator, and then it's just dividing by an 8. Well, at the beginning, that's going to be really nice. If like n equals 1 or something like that, that'll be really nice. And then we're like, okay, we'll get small numbers. But then as n gets very large, it's going to get much larger than 8. And this x plus 6, no matter what x is, it just gives you a multiplier. So it's not going to have something with n in this. And if this gets incredibly small, that's not really going to matter because this will get increasingly large. So immediately we can say that its radius of convergence is going to be 0, and it will only converge at a singular point. And we're like, what is that singular point? Well, it's going to be wherever that makes this 0, because the only place from our theorem that it'll either converge for all x, no x, meaning just 0, I guess. Well, when I say no x, I mean no x other than 0, or it'll converge for an interval. But this interval would just be a single multiplier and have nothing to do with n. So this n is just going, or square root n is just going to grow immensely, and this function, or this series, will not converge, except for one point. And now, my question for you is, where can we make this entire thing 0? I'll give you 5 seconds. Oops. 5 seconds. Well, that's going to be very easy. It's at -6, right? Because if we plug in x equals -6, well, that is square root n times 6, or -6 plus 6 to the n over 8, and it's the sum. Well, -6 plus 6, that equals 0, so then this just equals 0, and it converges. So for this question, it's only going to converge at -6, and it will have a radius of convergence of 0. And that is all I wanted to cover in today's video. Normally I do another practice problem, but I've completely run out of time. So, as always, my name was Logan. Thanks for watching. Have a great day. Yeah. Watch out.